Hey everyone, it is Mr. Vargas, back once again, this time helping out my Math 3 students with homework 6.6, the last lesson of this chapter, which involves using exponential and log functions. Now before we go into the homework assignment, there are some important formulas that I want us to have in our back pocket for solving these problems. The first one is the continuous compound interest formula, or better known as A equals P times e to the RT. Let's talk about what these different things mean in this situation. This A is the amount at time t. This P stands for your initial amount. T is your time that you're investigating, and R is your interest rate. Okay, so this is for working with money, finding out how much money you can make in a certain amount of time with a given interest, with that interest being compounded continuously. There's another very similar formula which works with population growth, and it follows the same model. We just use some different letters for this, and it's y equals a times e to the kt. Let me rewrite that. Kt. Okay, and very similarly to our compound interest formula, your A is the initial population, your Y is the population at time t, T is your time, and K is your rate of continuous growth. We can also talk about decay, so any type of decay, whether that be population or something related to carbon dating. You would just use the formula y equals a e to the negative kt. So this would be decay. Okay, without further ado, let's jump into some of your homework problems. Number 1 says, in carbon dating, use the formula y equals a times e to the negative 0.0012 t, where a is the initial amount of carbon-14, t is the number of years ago the animal lived, and y is the remaining amount after t years. Okay, and prompt A asks us, how old is a fossil that has lost 95% of its carbon-14. And my apologies, the formula is actually y equals a to the e minus 0 point another 0 in there. So 3 zeros, 1, 2 t. Okay, so let's set this up. So I've got y equals a e to the negative 0.00012t. And I want to figure out my initial value. Well, my initial value, everything starts out as a whole, so we're actually just going to replace my a with 1. Now, the fact that this fossil has lost 95% of its carbon-14 means that there is 5% remaining. Right? So 5% is the same as 0.05, and that kind of makes sense because after a certain period of time you would expect this that one whole to go down to about 5%, to go down to 0.05. So that's what's left over. So we can put that in for here, and we've got e to the negative 0.00012t. We've got everything we need to start solving this equation. Since this is just 1 times this, we can kind of ignore that 1 and just go ahead and natural log both sides to bring down the exponent. You get ln of 0.05 when you type that into your calculator. It's about negative 2.996, and that's, approximately equal to, well, what happens with natural log and our base e? Those things cancel out, and we can bring down our exponent. Awesome. So now it just becomes a matter of solving for t. Divide both sides by negative 0.00012 and divide the other side by the same, and you get t is approximately, when you punch this information into a calculator, you get approximately 24,964. So that means for this fossil to decay all the way down so that only 5% of the carbon-14 is left, it would take 24,964 years. Okay. Alright, on the second page of your homework assignment, we are asked to assume that population of gnats in a specific habitat follow the function p of t is equal to 17,000 divided by 1 plus 15 e to the negative 0.0082t. So part A asks us to graph this information, and we can do kind of just a rough sketch of this. I did use Desmos to help me out and Wolfram Alpha, but let's go ahead and make this like 2,000, 2K, 4K, 6K, 8K, 10K, 12K, and K stands for 1,000 here. I'm just being a little lazy. Okay, and then we want to look at time. We can do that going by years and hundreds. So let's do 100, 200, 300, 400, 500, that's t. And our y-axis, or p of t, goes here. So we've got our t-axis and our p of t axis. So just like any function, we could create a table of values. When in doubt, table it out, and then we can use our calculator to figure some stuff out. So, you could have my t here and my p of t here, and then what happens when I plug in 1,000 for t gets me some p of t, and that information would go right there. But just using our graphing calculator, we can see that this function kind of starts out around 1,000, and it progressively goes up. I'll use a different color. Let's use blue. So kind of slides up like this and then peaks and crosses over 14,000 and it's on its way. So that's good enough for that graph. What is the horizontal asymptote for part B? Horizontal asymptote. So basically, where does this function reach its maximum? And looking up at this equation, kind of the maximum is what's going to be on top here in the numerator. Since we're dividing this numerator by a denominator that has 1 plus another number, you can imagine that this is going to get really close to 0. So eventually you're just going to be dividing 17,000 by 1. So that is your maximum. If you had to kind of draw that asymptote, it would probably look like this, horizontal on your graph. So here I would say my horizontal asymptote is at y equals 17,000. Since, as time goes on forever and ever, once again, this term is going to become 0, so it would be 1 plus 0, which is just 1, and 17,000 divided by 1 makes 17,000. So that's my horizontal asymptote, and that also happens to tell me what the max population is. It's going to cap out at 17,000 gnats. And letter D, it asks, when does the population reach 15,000? Reach 15,000. Go back and circle my answers really quick, sorry. Okay, so here you could actually use that equation that they gave you before, and this 15,000 would take the place of your population at time t. So you would want to set this equation up as 15,000 is equal to 17,000 divided by 1 plus 15 times e to the negative 0.0082t. So this is the equation that you'd want to solve. I'm not going to solve it for you right now. You guys can try that on your own, but basically to get you started you would need to multiply this side by the denominator here, and then multiply the other side by that same denominator. Then you would probably need to use the natural log function to get rid of the base e, bring down that exponent, and then isolate for t. And that should give you the amount of time it would take for those gnats to get to 15,000. Alright, that's it for this video. See you next time. Good luck on the rest of the assignment.